Okay, so let's briefly or quickly summarize the discussion from last time. I was making a very quick review of manifolds because I wanted to emphasize one method to turn naturally defined spaces into manifolds. So let me summarize that. So if we have a set M and another set A, and suppose we have a countable subset of A, okay, and so we are given for each element in A, so for each alpha in A, there is given a subset U, so given subsets U in U alpha in M, V alpha in Rn, and bijective maps X alpha from U alpha to V alpha, such that the following holds. First, if I take the union of all these subsets of M, U alpha, over all those alphas in this countable subset, then this is enough to get the whole space M. So this covers. Secondly, all sets of the form U alpha intersect U beta, and then pushed forward using this map to Rn. So that is open in Rn for any alpha and beta. Okay. Thirdly, we have that going from one X alpha to another one. So if you look at U alpha intersect U beta, apply X alpha to it, then this is a subset of Rn. It's an open subset of Rn. And we do the same thing with the map X beta. So that's also an open subset of Rn. And then we can go from this set to that set by going X alpha backwards and then going X beta forward. So that's now a map, a bijective map, from this open subset of Rn to that open subset of Rn, and so it makes sense to demand that this is a diffeomorphism. It's a diffeomorphism. And finally, for any 2 points in M, I want to have one of these U alphas containing both. So for any 2 points, I want to have one of those charts containing them both. So there exists an alpha in A such that P and Q all contain U alpha. And if this is given to us, then this set M carries a unique topology and a unique differentiable structure such that these X alphas become charts. Then M carries a unique topology and differentiable structure. It's also unique differentiable structure such that the X alpha are smooth charts. So the Hausdorff property is hidden in here. The countable basis of the topology is hidden in the first statement because we can do with a countable set of charts, and these transition maps are smooth, which gives us a manifold structure. Okay, and as an example, we have seen that we can, for example, look at real projective space, which was defined as a set of all one-dimensional subvector spaces of Rn, which is just a set a priori, but then we have constructed such maps X alpha, and we have checked that this map is a rational map, so in particular it's smooth. So this turns this set of lines in Rn into a smooth manifold. Okay, any questions about this so far? So that's just a brief summary of what we discussed last time. Not right now. Good. So my next aim is to talk about bundles, about vector bundles and other bundles, space bundles, I should say, and other bundles too. But before I do that, I want to use a very uniform approach to the theory and not have to define all kinds of bundles again and again. And in order to do that, the language of categories is extremely convenient. And so this is why today I will spend the lecture on some aspects of category theory. And next lecture then we will apply this to discuss bundle theory. After all, characteristic classes are defined for vector bundles, so we need to know what we're talking about. All right, so the second part of the preliminaries is category theory. So, categories. So what is this category theory? So basically, it's a language in which we can express mathematical statements. It's like set theory in some sense. But there are many people who believe that eventually category theory will replace set theory because it has advantages. For example, for computer-checked provings, set theory is not really very well suitable. And there are people trying to develop programming languages which can encode proofs so that the machine can check the correctness of proofs. And this will certainly require a change of the way we are formulating mathematics. And so this category theory started in the 1940s in algebraic topology, and but it's now spreading and being used in many areas, including mathematical physics, quantum field theory, for example. So it's worthwhile taking a look at it. So what is this thing? First of all, what's a category? Let me first define what a category is. Also, a category consists of the following data. So the first thing is, so let me call the category curly C. So it consists of the following data. So first of all, I have a class of objects. A class of objects in the category. I'm not saying a set because I want to consider a thing like the category of all sets. And as you know, the set of all sets does not exist because you have these paradoxes like if you had the set of all sets, then you could look at the subset of all those sets that do not contain themselves. And then you ask the question, does this subset contain itself? And there are two possibilities which both lead to a contradiction. This is this famous Russell paradox. And so we cannot talk about the set of all sets. Instead, what we do is we talk about the class of all sets. So that exists. The class of all classes doesn't exist, but we don't care about that one, right? So this is why I'm writing the class of objects and not a set of objects. All right, so and the second thing that we need is whenever I have two objects, so for any x and y objects of my category, now I have a set called more category C, X, Y. That is a set. And in fact, there are different conventions here. Sometimes it's also defined to be a class rather than a set. And then if I demand that it's a set, then it's called a locally small category, whatever. But I don't want to go into this because this will be good enough for us. So the different, I'm just mentioning that there are different conventions at this point. And the third thing that we have is that we can somehow compose these morphisms. So for any x, y, and z, is given a map, taking an element here and an element in here, giving me an element in here, which is denoted by taking, well, we call this G and this element F, and this is being mapped to G circle F. And the terminology is that, well, the elements in here, so many elements in this thing are called objects of the category. Called the objects of C. And the elements in this are called the morphisms. From X to Y. And this is called the composition. Of course, this makes us think of maps and compositions of maps, and we will see examples in a moment. And in many cases, this will be the composition of maps, but not always. So that's just the terminology. And so these are the data that are given, and we have to satisfy certain actions. What are the actions? So now this is continued here, such that the following holds. First of all, this composition has to be associative. Meaning that if I, if I have the composition of 3 morphisms, then it doesn't matter which way we set brackets. So whenever these compositions are defined, right? So then the morphisms have to be in suitable morphism spaces, so they have to fit together. So I can only compose F with G if F is a morphism from X to Y, and then G is a morphism from Y to someplace. Let's say for suitable morphisms FGH. For all suitable morphisms FGH, we have this associativity. And the other thing is we have neutral elements. So for any object of C, there exists a morphism, which I call 1 subindex X, which is a morphism from X to X, such that if I compose it from the right, then I get this element, and if I compose from the left, it's the same thing. So where, now let's see, F is a morphism from some place to X, and G is a morphism from X to some place. So that these compositions make sense. So these are the actions. And before I come to examples, a few remarks about this. Namely, first of all, this element whose existence I have demanded here, so this is unique. Number 1. 1x is unique. So I could have put it to the data if you wanted, and it doesn't matter really, it's unique. Namely, if 1x prime in the morphisms from X to X is another one, then we do this extremely involved proof that we compose the two. Now I use that this is a left unit element, so the result will be 1x prime. But I can also use that this is a right unit element, so the result is x. So there you go. So this is the kind of argument we know from semester 1 when we started doing mathematics. Okay, so we can talk about the one element corresponding to the object x. Good, that's one thing. And another thing is that if I have a morphism f, so it's called an isomorphism. In this category, if there is an element in the opposite direction, a morphism in the opposite direction, which such that when I compose f and g, well then I go from y to x and then back to y, so that should be 1y, and if I compose it in the other order, then I go first from x to y and then flow back to x, so then it should be y, if there's such an element. Okay, and remark here, such a G is also unique if it exists. It doesn't always exist, this exists only for isomorphisms, but if it exists, it's unique. And the same kind of proof, so if G prime from morphisms from y to x is another one. So what do? We look at f composed with g composed with g prime. So that's x prime f g. Now we have to put parentheses, but it doesn't matter which way we do it because of associativity. And so since this gives me the identity of x composed with g, so it gives me g. And here this gives me the identity of y composed with g prime. And so which should also be the identity of x composed with g prime, which is g prime. So these elements are also unique if they exist. And then write f to the minus 1 instead of g. So if we are talking about maps, if these morphisms are maps, then this is the inverse map. But in general, in a category, the morphisms need not be maps, but still we can use this notation. So examples now. We make a table. So here's my category. Here are my objects. See, here are the objects. Here are the morphisms. So, well, for example, we could take the category of all sets. Yes? Are you saying that I should replace this by a y? Then I do it. Yes, good, thanks. So let's, the first example is the category of sets. So what are the objects? Well, the objects are just sets. So take all sets. And what are the morphisms? Well, for morphisms I could take all maps. Right? So that would be the set of maps from x to y. So that would be the huge category. In fact, since I'm talking here about isomorphisms also, let me introduce this notation here that by iso C of x, y, this should be the set of all morphisms which are isomorphisms. And then, what are the isomorphisms in this category? Exactly. Bijective maps. From x to y. So you see, the space of morphisms, and in particular also the space of isomorphism for two objects, can be empty. It's never empty if x equals y, because then we have this one element. But if x and y are different, then there's no guarantee that that the morphism set is non-empty. So one can also already see this in this example. So certainly, if x and y have a different number of elements, let's say finite and different number of elements, there's no bijective map. So that would be empty. But also this can be empty. When? Exactly. If y is empty and x is not empty, then there is no map. If x is empty, there's the empty map mapping nothing to anywhere. So that's okay. All right, good. And what else? Another example. Top. The topological category. In this case, the objects would be topological spaces. And the morphisms would be continuous maps. And what are the isomorphisms? Yes, these are the homeomorphisms from x to y. Is this the same thing as saying these are bijective continuous maps? So my question is the inverse of a bijective continuous map automatically continuous? For example, if you have a bijective linear map between two vector spaces, the inverse is automatically again linear. So what's a counterexample? Half open interval. Yes. Yeah. Wrap it up, and this would be wrap it a half open interval, wrap it up to a circle. This is bijective continuous, but the inverse is not continuous because at the break point you have a discontinuity. Yes, and in fact, so in this category of the language, there is no danger that you make the wrong definition here, because I mean we are never. This bijectivity makes sense for maps, but morphisms need not be maps. So bijectivity in general does not make sense for morphisms. So we are not even tempted in the categorical language to say that these isomorphisms are bijective continuous maps. Rather, we have to formulate it completely in terms of these compositions of continuous maps, and then it's made sure that the inverse map is also continuous. So in this sense, you see already that this categorical formulation prevents us from making mistakes sometimes. Okay, anyway, so then another category would be that of differentiable manifolds. Let me call this category diff manifold, so differentiable manifolds. And then this would consist of all smooth maps from x to y. What are the isomorphisms? Exactly. So those are the diffeomorphisms from x to y. Good. Then, what else do I have on my list here? Well, an important one is this one. Okay, so we fix a field K. K as a fixed field. And then we have the space of all, the category of all k vector spaces. The corresponding morphisms are linear maps. K linear maps from X to Y. And the isomorphisms are K isomorphisms in the sense of linear algebra, right? And in this case, I could actually say bijective K-linear maps, because then the inverse would automatically be K-linear. And then, of course, there are lots more categories. We will see some of them, just that we get an idea. So in this case, in these examples, our morphisms have always been maps. So in this case, the objects of the category were sets with some extra structure. But that's not necessarily the case. So let me give some other examples of interesting categories where the morphisms are not maps. For example, we could look at this. Let's look at the category where, so let's say the objects of my category, there's only one. It doesn't matter how I call it, let me call it asterisk. Only one object. Can't be much smaller than that, right? And now, assume that all morphisms in this category, so I can always go only from this to there, right? So there's only one set of morphisms here. So these morphisms, let's assume they are all isomorphisms. So assume that all morphisms are isomorphisms. Now what do we have? This object is not interesting. It's just one thing. But this set of isomorphisms might be interesting because we can do things with it. If you remember the definition of a category, there's a composition defined on it, and there's a one element defined on it. And what do we have? We have associativity, and by this assumption also we have inverses. So this thing is nothing but a group. Now, assume this, then these isomorphisms form a group. No matter what the elements are, they are not maps anymore. So they are some things, group elements. Conversely, if G is a group, then put the objects of my category to just consist of one element, of one object, and put the morphisms to this group. And take the group composition as your composition of morphisms. Then this will give you a category with just one object where all morphisms are isomorphisms. So in other words, a group is nothing but a category where you only have one object and all morphisms are invertible, isomorphisms. So that's the formulation of the concept of a group in categorical language. Now, this can be generalized now in various directions. So, for example, you could drop this assumption that all morphisms are invertible. So again, we have only one object. But now we do not make this assumption anymore. And then we can still compose in here. We still have this one element in here, but we do not necessarily have inverses. So that's a weakening of the concept of a group, but that also has a name. It's called a monoid. Then morphisms in this category form a monoid. For example, natural numbers with the addition would be such a thing. So you could have the category with one object, and the morphisms consist of the natural numbers, and the composition consists of addition. In this case, morphisms have nothing to do with maps. Okay, that's one possible direction where we can generalize this. Another direction would be to say, to not drop this assumption, but to drop the first assumption. So if objects form a set rather than a class, and so not just one element, but not too many, so that's still a set. And but we still assume this one, and morphisms should all be isomorphisms. For all objects. Then this also has a name. Then C is called, someone know? It's a groupoid, exactly. So you can think of a groupoid as a group, just that you cannot always compose the elements. You can compose the elements only if they fit together with these morphisms. Well, that's a groupoid. Yes, okay, so these algebraic concepts can also somehow formulate it in this categorical language. All right, now one or two pieces of notation here. So if C is any category, then we can derive another category from it. So then let C circle be the category with the same objects. So the objects of C circle should be the same as the original object of C, but we reduce the number of morphisms. Namely, we set the morphisms in C circle between two objects to be the isomorphisms only of the original category. And since the inverse of an isomorphism is again an isomorphism, the inverse of an element in here will be still contained in here. So this means that this is then the same thing as also the isomorphisms of C circle. So in other words, we throw away all those morphisms that are not isomorphisms, then we are left with a category where all morphisms are isomorphisms. And this will be denoted by this symbol. Okay, that's one thing. And another one is the Cartesian product. So if C1 up to Cn are categories, then we can define Cartesian product of these categories. I. So what are the objects? The objects in this category, imagine these are just tuples of objects in the original categories. So these are tuples where each xj is an object of Cj. And what do we do with morphisms? Morphisms in this new category Cartesian product. So this should now be act between two such tuples. And this is just a tuple of morphisms between the corresponding things. So that's tuple f1 up to fn, such that each fj is a morphism in Cj and it's tuple. It's a bit deep. I will need this notation too. Good. All right. So I hope. But I knew someone would ask, what is the difference between a class and a set? Okay. Now functors. Functors. So suppose we have two categories. So let C and D be categories. Then a functor from C to D consists of the following data. So first of all, I have a map from the class of objects in C to the class of objects in D. And the map is just an association that associates to each object here and object there. And now please don't ask me what a map is, right? Because that's also debatable. And I just written, so functor, let me call it curly f. And this will be written as taking an object here and applying to it f of x. So to each object, there's a new object in the second category, and similarly for morphisms. So for any two objects in my first category, I have a map from the set of morphisms in C, x, y, to the set of morphisms in the target category between the corresponding target objects. So I map objects and I also map morphisms. And this was written as f is being mapped to curly f of f. And what do we need for actions such that first condition is this mapping on morphisms preserves composition whenever it's defined, of course. So for f1 into the blah 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 and f2 in blah blah blah, so that things can be defined. And secondly, it preserves these one elements. The one element of x is the one element of fx. So these are the conditions. That's a functor. So the functors set up relations between different categories. So let's look at examples. Okay, good point. Yes, the question is there a distinction between covariant and contravariant functors? Indeed. So what I've defined here is a covariant functor. And so if one doesn't say anything, one usually means a covariant functor. One could also define contravariant functors, where this order is reversed. It's reversed here too, but we won't need this. This is one not making the definition. In a way, we will see a contravariant functor come up in a moment, but I will apply the trick to avoid using that concept. Okay, and examples. So there's a whole first set of examples of functors related to these first examples here, where we had categories defined by sets with additional structure, and the morphisms were maps with additional properties. And in such cases, very often you have forgetful functors. Forgetful functors. example, you have one from top to set. So what you do, you take a topological space and you forget the topology. Just consider it as a set. And you take a continuous map and you forget that it's continuous. Just consider it as a map. Similarly, you can have, I don't know, something like forgetful functor from differentiable manifolds to top. You take a manifold, you forget that it's a manifold, you just keep the topological space. The smooth map is in particular a continuous map, so I have that. Or, for example, also you have a forgetful functor from real vector spaces to differentiable manifolds. So, okay, I should say finite dimensional real vector spaces. So that's the category of finite dimensional real vector spaces, because each real vector space is in particular a differential manifold, and a linear map is in particular a smooth map. Or you could also have a forgetful functor from complex vector spaces to real vector spaces, where you just take a complex vector space and forget the multiplication with I and consider it as a real vector space. And the C linear map is in particular R linear. And so you have lots of these forgetful functors. And typically it's obvious what one means if one says a forgetful functor from this category to that. So we have those. All right. What else? Questions? No, actually, this is not a. Okay, I never made a definition of what a forgetful functor is. It's understood that in these examples, it's clear what's meant by it. So you could come up with a definition. You could say, okay, if my objects are tuples consisting of sets and blah 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 certain structures, and you just drop off some of these structures, then that's a forgetful functor. For example, a topological space is a pair of a set and a topology, and then you just drop the topology, and you forget extra conditions on the morphisms. You could come up with the definition, but I think it's pretty clear what's meant. Okay. That's not what I wanted. Okay, yes. Other functors are of a more algebraic nature. For example, you could have a functor from vector spaces over some field to vector spaces over the same field. And now what you do is, on the level of objects, you take an object, vector space, and you replace it or map it to its dual space. Okay, and what do you do on the set of morphisms? Well, the only natural thing what you could do is take the adjoint map acting on the dual space. And now you should complain. Because this is contravariant, not covariant. Right? If you take the composition of two linear maps and take the adjoint, then the order is reversed. So that would actually be an example of a contravariant functor. But I told you I don't want to talk about contravariant functors, so what I'm doing instead is I'm looking only at isomorphisms here. Restrict myself to isomorphisms. And then I take the dual of the inverse. Taking the inverse will flip it again back. And then it's a covariant functor. So that's what I'm doing. I could define the opposite category where the composition is turned around. I could do that too. Yes. Yes, so that's a kind of algebraic function. Other things, for example, you could take another one of this type here would be to take again vector spaces, but now I take a Cartesian product to associate to this another vector space. So on the level of objects, I have a pair of two vector spaces, and I associate with this the direct sum, which is another vector space. And on the level of morphisms, I can take a pair of linear maps. So F1 maps x1 to y1, F2 maps x2 to y2. So I need now something which maps x1 plus x2 to y1 plus y2. And it's obvious how to do that. I just take the direct sum. So that would be a functor which describes taking direct products. You could also similarly do this with tensor products or with lots of wedge products and stuff. So for example, similarly, tensor product, and you can also take more than two entries. And we have level of objects, take the tensor product. On the level of morphisms, so in other words linear maps in this case, I take tensor product used on the tensor products. And for example, vector k to itself, I could x map to some exterior power of x, lambda L x, where L is fixed, some fixed natural number. And then correspondingly, a linear map from x to y would be replaced by a linear map from lambda Lx to lambda Ly, which is just given as the corresponding induced map of L of f. And so on. All these algebraic operations are also functors. All right, so now I will look at a particular class of categories and also a particular class of functors, which we will need for our bundle theory. Definition: a category C is called, actually I would have loved to call it smooth, but unfortunately the terminology smooth category already exists and means something different. So I have to come up with a different name, and so I like it, and then I call it C infinity suitable. Suitable for our purposes. And when is it called C infinity suitable? Namely, first of all, I require that every object, so every object in category X is a differentiable manifold. So for example, if the category is the category of differentiable manifolds, that's certainly true. But not only then, it's also true in many other cases, like real vector spaces, finite dimensional vector spaces, for example. And it's also, you have this forgetful functor to manifolds. And so basically, on the level of objects, I am requiring to have this forgetful functor. And on the level of morphisms, for any two objects, that, well, morphisms and are all isomorphisms. That's one thing. So like for a group point, I want to have that everything is invertible. Plus, these things, these morphisms, are in fact diffeomorphisms of differentiable manifolds. So there are two things. I have a forgetful functor from my category to the category of differentiable manifolds, meaning that all objects carry the structure of a differential manifold, and all morphisms are smooth. Plus, I want to have that all morphisms are invertible. So these are the conditions. So, in particular, or one could rephrase this definition as saying we have a forgetful functor from our category to the category of differentiable manifolds, and this isomorphism thing I could rephrase as saying that these two categories coincide. So that's another way to say this. Yes, everything in here is invertible, but this equality is in general not true. So, for example, if you look at the category of finite dimensional real vector spaces, then the morphisms are linear maps, but they don't have to be invertible. So the category of finite dimensional real vector spaces would not work. But if I reduce the set of morphisms to isomorphism, then it works. So this is an additional assumption on the category, that all morphisms are isomorphisms. I mean, then all of them have to be smooth, so that's why they have to be different morphisms. Okay, so what are examples of such infinitely suitable categories? Well, you could take the category of differentiable manifolds, except that this condition is not satisfied, right? The morphisms were all different, all differentiable, all smooth maps, but we can compare this by just reducing to all invertible morphisms. Then another example would be to say, okay, let's take real vector spaces. Every real vector space is a manifold, and so finite dimension. And every linear map is a smooth map, but they are not all isomorphic, not all invertible. But we can just fix this by removing everything that's not invertible. Or we use complex vector spaces. First, forget the complex structure, go to real vector spaces, and then we are here. But of course, we also need to restrict to everything that's to isomorphisms. Then another thing would be a category. So that's another. I'm listing now categories which would be important for bundle theory. So let me take that of Euclidean real vector spaces. So objects here are finite dimensional real vector spaces which carry a scalar product. And so objects are finite dimensional Euclidean vector spaces, which means they are real and they carry as a Euclidean scalar product. And morphisms, as morphisms I take isometries, so linear isometries. So since they are isometries, so they are invertible. The inverse is again a linear isometry, and these are certainly smooth maps. These are smooth manifolds, so that's one such category. Similarly, the corresponding complex analog would be Hermitian vector spaces. So here the objects are finite dimensional Hermitian vector spaces. And the morphisms are again linear isometries. Now let's see linear isometries. That would be another such category that we will need. Now, what else? I could take oriented finite dimensional real vector spaces. So the objects are oriented real finite dimensional vector spaces. The morphisms are orientation preserving isomorphisms. Of course, in all these examples, you have to make sure that the composition is still okay. So if you compose two orientation-preserving isomorphisms, of course, you get again an orientation-preserving isomorphism, and the identity map is an orientation-preserving isomorphism, etc. Right? But this is all these things are obvious in these examples. Good. And here's an interesting one. Example 7. Namely, you fix a Lie group and now G, and now I can consider the category G if manifold. So what are the objects? The objects are pairs of differentiable manifolds and a right G action on the manifold. Objects are pairs, x, rho. Rho stands for right because I'm going to use a right action. X, rho, where X is a differentiable manifold and rho is a right action of G on X, so that I could say it's a map from G, so it acts by diffeomorphisms on X, and so this is a group and this is also a group, and it's a anti-homomorphism. Because I want to have a right action. If I had said it was a homomorphism, it would be an action. So here the notation is now right. Instead of rho of G, now rho of G will be a diffeomorphism, and you can apply this to a point of the manifold little x. Instead of this, you write simply x dot G. So the G stands on the right of the x, and you want to have the following. Now if you multiply with a G and then result with another group element H, then what would you get? Well, you would get rho of H applied to X times G, which is rho of G applied to X, right? And since I demanded that this is an anti-homomorphism, this composition will be the same as rho of, and now I have to turn things around, GH applied to X, which I can then again rewrite as X times G times H. This is what I want to have. I don't want this order here to be turned around. This is why I need that this is an anti-homomorphism. So here I have to turn things around. Okay. So these are the objects. Well, no, there's another condition on this action, namely such that the map from G cross X to X, mapping G, X to X times G, so that is smooth. And I want to have this action simply transitive. What does that mean? So that's one property. And the other property is simply transitive. That means the map, so for any point in my manifold X, the map from G to X, mapping G to X dot G is a diffeomorphism. In particular, it's bijective. In other words, this manifold X is diffeomorphic to my Lie group in particular. So simply transitive. Transitive means between any 2 points, for any 2 points in the manifold, you can find a group element mapping the first point to the second point. And this is made sure by this thing being surjective. But the corresponding group transformation G is also unique. That's the simply transitive thing. And this is the fact that this is an injective. So this is you could briefly call this a simply transitive G space, smooth G space. So these are the objects and the morphisms in this category. Well, there are smooth maps from one such G manifold to another one. So morphism from X row to Y row tilde. It's just one smooth map or diffeomorphism that preserves the group action. So that is a diffeomorphism F from X to Y such that F of X G is equal to F of X. So here this dot comes from the action on X, and this dot comes from the action rho tilde on Y. Is this clear? Okay, so that's another such category. Okay, and now these are these suitable categories, and each of these categories that I've listed here will lead to another kind of bundle. Now, the corresponding type of functor between such categories, so let C and D be C infinity suitable categories. A functor F from C to D. Maybe I should make another definition first. Sorry. Let's keep this there, but I need another definition first. Namely, to be continued, definition. So let C be a C infinity suitable category. Now, and M a manifold, a differentiable manifold. Now, a map from the manifold to the morphisms in C between two objects. So X and Y are any objects. So from a manifold to such a morphism set is called smooth. Now you see, in my category, x and y are manifolds, but the morphism set is not a manifold. So for example, if this is if you look at the category of differentiable manifolds, then this morphism set would be the set of all diffeomorphisms from x to y. And this is in general, it's an infinite dimension, it's either empty or an infinite dimensional space. And so it's not clear what we mean by a smooth map from a manifold into such a thing. But in this case, actually it's easy to see what it means. It's called smooth if the map, let me call the map phi, let's say, if the map phi check, which is defined on m cross x to y, and phi check takes an element of m and an element of x, and what does it do to it? Well, m can be sent to a morphism here via the map phi. Now I have a morphism from x to y, so let's just apply the result on x, and then I get an element in y. And now this is a map, this is a manifold, this is a manifold, this is a manifold. Now it makes sense to talk about smoothness. So if this map phi check is smooth. So, okay, now we know what it means for a map from a manifold to such a morphism thing. Even if that thing is not a manifold, we know what it means for that thing to be smooth. Now once I have that, I can define what a functor, when a functor between two such infinitely suitable categories is smooth. Smooth if for any smooth map from some manifold to the morphisms in C, for any smooth map, the map that I get by composing with the functors again smooth, the map M to morphisms, so let's call it capital F. These are now morphisms in D. So if I call this, what was it called, phi? If this map is smooth, then the map given by composing with the functor is also smooth. So you could say, if you have a smooth family of morphisms in your first category and you apply the functor to everything, then you get again a smooth family. Makes sense. So what are examples of such smooth functors? So we had one of these algebraic functors that we were looking at. So namely, the functor was given on finite dimensional real vector spaces, and it was given by this going to the dual space. X is being mapped to X star, and the morphism is mapped to the inverse star. So now I'm claiming this is a smooth functor. Why is that? All right, so what do we have to do? Now suppose we have such a thing, so that M is a differential manifold. I have to put a circle on top, otherwise I cannot invert F. Indeed. Thanks. Okay, now suppose I have such a thing, so it's a differentiable manifold, and phi, a map from M to the morphisms in this category. So let me call it C, X to Y. So this is the set of all set of all invertible linear maps from X to Y. Well, yeah. So now, what does the smoothness mean? So let this thing and let this be smooth. Actually, in this case, the morphism space is in fact a manifold. Namely, in this case, if we choose bases E1 up to En of X and E1 tilde up to En tilde of Y, same dimension because otherwise there is no isomorphism. And use this basis, or maybe I do this differently. You choose an isomorphism from X, let me call the first one psi X, from Rn to X. So right, this is some finite dimensional vector space, so there's an isomorphism, real vector space, so there's an isomorphism from Rn to it, and similarly for the other one. And the n has to be this, the dimension is the same, otherwise there is no isomorphism here. And now, then this thing can be mapped to GLN, the general linear group, so invertible n by n matrices, by saying, well, I take the matrix that represents the linear map in these bases. So, in other words, F is being such a morphism, this C. Such a morphism is mapped to, well, the matrix I consider as a linear map from Rn to Rn, so let me first go from Rn to X, then from Rn to X, then compose with the F, then we land in Y, and then go back to Rn, so psi Y equal -1. So this is now a linear map, an invertible linear map from Rn to Rn, and this is naturally identified with the matrix GLN, right? So that's how I understood it. So this way, so that's an open-dense subset of Rn squared, and now if we do that, then phi being smooth is equivalent to saying that the map phi composed with this one, so let me call this capital psi, composed with capital psi from M to GLN is smooth. Little exercise. I explained what it means for this thing to be, for phi to be smooth, and I'm claiming if I identify this space in this natural manner with GLN, here this lands me in some Euclidean space Rn squared, so it makes sense to talk about smoothness for this, but this is the same thing. And now, this is just a reformulation of smoothness of such a family in this particular example, and for this particular category. And now let's look at the functor that we are looking at here. So it's this one. And now this map corresponds to, after composing with capital psi, to a matrix. So it's from GLN to GLN. Now take the inverse matrix and then take its transpose. And you see, this is a smooth operation. So if you have a smooth family, a mapping to these matrices smoothly, and then you perform this, and the result is again smooth. The inversion of a matrix is smooth because it's given by 1 on the determinant. The determinant is a polynomial expression in the entries of the matrix times certain subdeterminants. So inverting a matrix is a smooth operation in the entries of the matrix, and transposing is surely too, because it's just putting the entries at different places. So that is a smooth map. So that is smooth. And so you can again get a smooth family, and so it's a smooth functor. And similarly, similar arguments can be made for all the algebraic functors that I've shown. So similarly, for the other algebraic functors, which were like taking the direct sum, taking the tensor product, taking an exterior product, and so on. You can always identify your spaces with your morphisms with matrices after choosing bases, and then you see that taking these things is always rational functions in the original entries at the worst. It's always smooth. Is this clear? Okay, and the last thing, and then time is up anyway. The last example is of a somewhat different nature, namely, it's a smooth functor from another example. So we go from finite dimensional real vector spaces, all invertible, to our differentiable manifolds with the group action, and the group action is indeed the action by GLN. So that's my Lie group. GLN is a Lie group in particular. So, and how does this work? Well, if I have a vector space on this level of objects, what do I associate to X? To X I associate the set of all bases of X. And now there's a natural action of GLN on that. Take a basis and just multiply it with this matrix, then you get a new basis. So the GLN action is just given by the transformation matrix that transforms one basis into another. Yeah, I have to fix n for fixed for a fixed GLN. I mean, I could do something like take the union, so these GLNs can be naturally embedded in one another. You can pass to a limit and you get GL infinity, and then you could treat all of them simultaneously. But then the limit would not be a finite dimensional Lie group, and so that's easy for us. It's easier to just fix the dimension. Makes sense anyway, because all our morphisms are invertible, and so if you have two vector spaces of different dimension, there's nothing that connects them anyway. So we should fix the dimension. Yeah, thank you. Yes, so this is being mapped to the basis, and if you have a morphism F, it's also clear what it does. You just apply it to all basis vectors, and then you get a basis of the target vector space. Right? F is being mapped to the map which maps a basis of X, V1 to Vn to the corresponding image basis. So that's a functor. Associate to a vector space all its bases. And this is such a smooth functor from the category of n-dimensional vector spaces, invertible morphisms, to GLN manifolds. Okay, so my time is up. Thank you. And next time we will apply this language to discuss bundles of manifolds, in particular vector bundles.